Welcome to the Explainer. Today, we are digging into generative AI. You know, that tech that feels like straight-up magic? It can whip up these incredible images, videos, and even text from just a handful of words.
So you just type in a few words, something like Manar on the beach, and boom. In just a couple of seconds, a machine spits out this, a super detailed photorealistic image. It's wild.
I mean, come on, a simple phrase just created a whole world. It really does feel like magic, doesn't it? But of course, it's not. So let's pull back that curtain and really get into how these amazing systems actually do what they do.
Okay, so we're going to break this down. First, we'll look at how these systems learn to create stuff, and then how they learn to understand what we want them to create.
Right, let's start with the creative engine itself. At the heart of most of the image generators out there, you'll find one of two main approaches. Either something called a Generative Adversarial Network, we'll just call them GANs, or diffusion models. So first up, GANs. The best way to think about a GAN is to imagine a game, a high-stakes game between two competing AIs. You've got an art forger, which we call the generator, and you've got an art detective, the discriminator.
Okay, so here's how the game works. The forger, the generator, its whole job is to create fakes from scratch, just random noise that are so good they can fool the detective. And the detective, the discriminator, its only job is to get better and better at spotting those fakes by comparing them to a huge library of real images. They're locked in this constant battle, and with every round, the forger gets smarter and the detective gets sharper. This whole adversarial process is what forces the forger to become a master at creating images that are just incredibly realistic.
All right, so that's GANs. The other big approach, which is used by models like Stable Diffusion, is totally different. This one is more like a sculptor, starting with a big, messy block of marble. Except, the marble is just pure, random, staticky noise.
So how does it work? Well, it starts with an image that's just pure static. Then, the model looks at it and predicts what some of that noise is, and then it subtracts just a tiny bit of that predicted noise. And it does this again, and again, and again, sometimes 50, even 100 times. With each step, it's like it's chipping away at the static, slowly revealing a clear, detailed image. It's literally sculpting a picture out of chaos.
So you can see there's a pretty big trade-off here, right? GANs are super fast, but they can be a bit temperamental. They can run into something called mode collapse, which is basically when the forger AI gets lazy and just starts making the same few kinds of images over and over because it knows they work. Diffusion models, on the other hand, are way more stable and they give you a much more diverse range of images. The downside? They're slower, and they need a lot more computational horsepower to run.
Okay, so having a creative engine is awesome, but it's really only half the story. The AI also has to understand what we're asking for, right? It needs to get our instructions. And that's where large language models, or LLMs, enter the picture.
So, an LLM doesn't just happen overnight. It goes through this whole training pipeline. First up is pre-training. Think of this as the model being like a toddler that gets to read the entire internet. It just soaks up grammar, facts, patterns, everything. Then it goes to a kind of specialized school called instruction fine-tuning. This is where it learns to actually follow commands and answer questions. And finally, there's alignment. This is where it basically learns its manners, making sure its responses are helpful and harmless based on human feedback.
But let's pause for a second. What does a model actually know after just that first stage? After it's read the whole internet, but before it goes to that specialized school? Let's look at a concrete example, because the difference is pretty wild.
So, we're going to ask a simple question to a pre-trained model. What is the capital of France? Now remember, at this point, all it knows are language patterns. It hasn't learned how to actually follow an instruction yet.
And look at the response. It's grammatically perfect, but what? It completely ignores the question. See, it's not thinking about the answer. It's just predicting what words are most likely to come next in a sentence that starts with, "What is the capital of France?" It's basically playing a massive, internet-sized game of word association.
Okay, now let's ask that exact same question, but this time to a model that has gone through that next step, the instruction fine-tuning. There it is. The capital of France is Paris. The difference is just night and day, isn't it? By training on all those examples of questions and good answers, the model has learned to be actually, useful.
But being helpful is one thing. The model also has to be harmless, and that is a massive challenge. Because remember, it was trained on the internet, and the internet, well, it's filled with all kinds of biased, toxic stuff and flat-out dangerous information.
And this is exactly why that final step, alignment, is so incredibly important. Without it, things can go wrong. For example, OpenAI's own safety reports showed that an early, unaligned version of GPT-4 was capable of responding to unsafe prompts, like how to synthesize dangerous chemicals. That's a huge problem.
So to fix this, developers use some really clever techniques to align the model with human values. One of the most important methods is called reinforcement learning from human feedback, or just RLHF for short. It's basically a system for teaching the AI what we humans think is a good answer.
And the way RLHF works is pretty fascinating. It starts with real people. These human evaluators look at a bunch of different AI-generated responses to the same prompt, and they rank them from best to worst. Then, all of that ranking data is used to train a whole separate AI called a reward model. Its only job is to learn how to predict which answers the humans will like the most. So this reward model basically becomes a judge or a coach for the main LLM, training it to generate responses that will get the highest possible score for being helpful and harmless.
Okay, so we've looked under the hood and seen how the machine works. Now let's zoom back out and talk about the bigger picture. Because like any truly powerful tool, generative AI brings with it both amazing promise and some really serious peril.
On the one hand, you have this incredible promise. This tech could totally revolutionize industries, supercharge creativity, make things way more efficient. But on the other hand, there are huge risks. We're talking about the potential to spread misinformation like wildfire, to create convincing, malicious deepfakes, and to hard-code our own societal biases right into the algorithms.
And look, these aren't just some far-off theoretical dangers. We've already seen what happens when AI and user data are exploited. Just think about the Cambridge Analytica scandal. That was a perfect example of the ethical lines that can be crossed, raising huge questions about privacy, about consent, and about who is ultimately held accountable. And all of this leads to the biggest, most important question of all. At its core, generative AI is just a mirror. It reflects the mountain of human data it was trained on, all of it, the good, the bad, and everything in between. So the question we're left with is this. As this mirror gets more and more powerful, who is responsible for the reflection we see? Ultimately, that responsibility has to lie with us.